Okay, so this is section 3.4, which is elemental analysis, percentage of carbon, hydrogen, and oxygen. Okay, so a hydrocarbon is a compound that contains carbon and hydrogen only. When I combust it, I burn it in the presence of oxygen to form carbon dioxide plus water. Okay, and so this image down here shows this. You see I have oxygen being pumped in. This is inside of a furnace, so it's basically like an oven. Okay, I have copper pellets to help. This is kind of like the catalytic converter on your car. This helps convert it all to carbon dioxide and water. And then I have basically a drying agent, which is calcium chloride. And so what happens is that the sample burns, any ash may be left behind, but if it's just a hydrocarbon, it should not have any ash. Goes through, the gas is being pushed through this, it bubbles through this tube, and any water as steam is absorbed inside this tube. So I measure the mass before the experiment and after the experiment, and that tells me how much water has been absorbed. Anything but water, so any extra oxygen or carbon dioxide, continues to travel through the tube. And then I have a second tube here that's sodium hydroxide. CO2, when it goes into water, forms carbonic acid, so this neutralizes the sodium hydroxide, so I can determine how much CO2 then was there. And again, then the excess oxygen comes out. So it's important to remember that I cannot get oxygen because of the fact that I'm pumping oxygen in and oxygen's coming out. I cannot find the mass of oxygen using this experiment. Okay. Also, from last chapter, we had balancing reactions. Okay, so this is for any hydrocarbon. So I have X and Y here. So you see that the X becomes the X as a subscript here becomes the coefficient for the carbon dioxide, and the Y for the hydrogen. Because water has 2 hydrogens per 1 molecule, it becomes whatever the subscript for Y is divided by 2 becomes the coefficient there. So what this means is that for every 1 mole of carbon that I burn, 1 mole of carbon dioxide is formed. And for every 1 mole of hydrogen that I burn, a half a mole of water is formed. Okay, and these 2 things are going to become important in the calculation. All right, and so I'm just going to basically show you how to do the calculations. So number 64, this is the only problem like this, and it's fairly complex. Phenol is commonly known as carbolic acid, which used by Joseph Lister as an antiseptic for surgery in 1865. So basically this was developed during the Civil War. Its principal use today is the manufacture of phenolic resins and plastics. So the combustion of a 5.23 gram sample. Now if you look at this problem in the book, it has it as milligrams. I want to change it to grams just for simplicity. So 5.23 grams of phenol yields 14.57 grams of carbon dioxide and 3.01 grams of water. Phenol only contains carbon, hydrogen, and oxygen. So what is the percentage of each element in the substance? And that should be a question mark. Oh well. All right. So again, I'm going to pull out the information and I'm going to pull out the numbers. So 5.23 grams is the mass of phenol. The mass of carbon dioxide was 14.57 grams. The mass of water was 3.01 grams. Things I'm also going to need for this problem is I need the molar mass of carbon dioxide. Okay, so I did this the same way as I've been showing you. It's the mass of 1 carbon, which is 12.01, plus 2 times the atomic weight of oxygen, which is 32. So the 12 plus the 32, 12.01 plus 32 gives me 44.01. The mass of the water, still got in the same way we've been practicing. I have 2 hydrogens, each hydrogen is 1.01, and of course oxygen is 16, so when I add that up I get 18.02. So I'm just showing you what the masses are, but you do the calculation the same way. Of course I have mass of carbon, 12.01, that's just the atomic weight, and the molar mass of hydrogen is its atomic weight of 1.01. So the first step is to find the mass of carbon. Okay, so I'm going to start with my mass. Carbon came from which one of these 3 masses? Well, phenol has carbon, hydrogen, and oxygen. Water doesn't have carbon in it at all, so I'm going to start with the mass of carbon dioxide. So this is my mass of whole here. Okay, so to find the percent of each element, I'm going to use this as my mass of whole. But I can't use carbon dioxide because I just want percent carbon. So I have to change the mass of carbon dioxide to mass of carbon. So I'm going to start with the 14.57 grams of carbon dioxide. In order to compare, if you go back to the last slide, you'll notice the fact that the comparison was in moles. So this is building on what we did on Monday, and we did worksheets on Wednesday. The fact that we have to build this up to be it was in moles. So to go from grams to moles, I have to divide by the molar mass. So I'm going to divide by the molar mass of carbon dioxide. So that gives me the moles of carbon dioxide. Then, also based on the last slide, you'll see the fact that 1 mole of carbon was equal to 1 mole of carbon dioxide. So this now changes it. So I'm no longer in carbon dioxide, I'm only talking about carbon. But I'm looking for the mass of carbon, so now I need to go from moles of carbon to mass of carbon. So I need to multiply by its molar mass. And when I do that, I get 3.97. So I enter this as being 14.57 divided by 44.01. 1 to 1, I don't need to do that, it's 1. Times 12.01 gives me this. However, you don't need to enter this in your calculator, but you do need to show this in your work. Okay, gives me this. So then the percent carbon, again, this is my part now, over, like I said, this is my whole. So the percent carbon is the 3.976 grams of carbon over the total mass of 5.23 times 100 gives me 76.0 to 3 significant figures. Okay, for the hydrogen, okay, phenol again is my whole, so it has both carbon, hydrogen, and oxygen. So that's my whole. Carbon dioxide doesn't have hydrogen in it, so I'm going to start from water. So for the mass of the hydrogen, I'm going to start with my mass of water. It's 3.01 grams. Again, to be able to compare amounts, I cannot use mass. I have to use moles. So to get to moles of that, I have to divide by its molar mass of 18.02. So I divide by 18.02. This time, though, if you go back to the previous slide, which I can't do because of all this animation, the fact that the previous slide said that for every 1 mole of hydrogen that's burned, I produce half a mole of water. Well, if I reverse that and I say that then there's 2 hydrogens for every 1 water, that's what I have as this ratio. 2 hydrogens for every 1 mole of water. You could put in here, if you want to stick to that, the fact that for every 1 mole of hydrogen, I have 0.5 moles of water. That also works. Okay, and then I'm still trying to get to the mass of hydrogen, so I have to multiply by its molar mass or atomic weight of 1.01 grams of hydrogen. So it's going to be 3.01 divided by 18.02 times 2, if you want to, divide by 1 times the 1.01. This is important to note that for this and for the rest of the entire year, 1211 and 1212, that the molar mass is always going to be for one species, okay? This is called a mole to mole ratio, and we use that to take into account when there's a different amount of them. So when I do that calculation, I get 0.3374. And again, to find the percent hydrogen, it's going to be the mass of the hydrogen from here, divided by the mass of the phenol times 100, and I get 6.45. As I stated in the last slide, yes, there's oxygen in the CO2, there's oxygen in the water, but the experiment has oxygen coming in there, so I can't get the amount of oxygen in the compound from that. Instead, I'm going to use subtraction. Okay, so on the last section, the last video, I showed the fact that all the percentages have to add up to be 100. So to find the mass percent of oxygen, I'm going to take 100 minus the mass percent of the carbon, the 76, minus the mass percent of the hydrogen of 6.45. So the mass percent of the oxygen is 17.5. So there are 3 answers for this problem: 76.0% for the carbon, 6.45% for the hydrogen, and 17.5% for the oxygen. Unfortunately, that's the only problem that is like this in the book, so I don't have a separate example for you. But you can go back and rewind this video or pause this video per each step to understand it. But this is the end of that video.